right, folks, today we have gathered for the Sunday paper reading session. The topic today is interesting breakthrough work that was done by OpenAI group. This work is called the DAL-E. DAL-E is a sort of portmanteau, the combination of two words. One is the great artist Dali, and I believe his full name is Salvador Dali. Is that right? I think so. Kate, is
That's
this
right.
Salvador Dali? Yeah.
Yes.
And the lovely Pixar movie Wall-E. So Dali, the great artist, and Wall-E, the movie, together make Dal-E. Dali is it's one of the emerging body of research. This one is very, very interesting. What it does is you give it a prompt, a textual prompt, or maybe a little bit of an image uh, combination, the typical thing that you would do to a transformer. So think of a standard transformer model that we covered in our previous sessions. If you go back and remember all of the BERT and the attention is all you need and all the things that we covered and the visual transformers. The fundamental thing is you give it a prompt, you give it some input, and then you have an output. In particular, here, what we are talking about is using GPT-3. Now, just to remind you, remember we have the full transformer as an attention is all you need kind of a diagram with its encoder and decoder. Now, at some point we talked about BERT. BERT more or less uses the encoder part of it only, architecture, and it evolves from there to do its work. And the GPT family, they started with only the decoder part. And what's the difference between the decoder part and the encoder? Encoder, you have input, and it sort of does all this attention layers and a few feed forward layers, and then it produce. You know, remember all of this K, V, Q, and all of that. We won't go into that, but it produces a vector, those final vectors of K, Q, V, and then that's the encoded data that finally goes um, into the decoder in the full attention model. What does the decoder do? Decoder takes the output, the encoded output, or the encoded information. Then it takes a bit of the, again, the input, and quite often the input is the previous output. So there's an autoregressive cycle to it. It takes it back and then combines the two together. And what it does is it produces, encodes decodes the abstraction, except that when it decodes, the classic language model is you encode English into a sort of an abstraction, English sentence into an abstraction, into uh, those vectors. And then what comes out word by word, token by token is, let's say, French comes out. Right? A French translation comes out. And the whole point of attention was that words can pay attention to each other because they, in some sense, understand where to look. Right? What, how to do it. So the French sentence comes out looking the right way. And we won't cover all of those things. We have covered it many times. Now, that's how this thing goes. Now, again, GPT is only the decoder part of it, right? So you feed it to something that you have encoded, and then you also take the output, some of it you feed back and so forth. So that is the decoder, and that's the GPT. Now, GPTs have been, and BERT also, both are dominant implementations of transformers. There's a whole family of BERT. All sorts of BERTs are there, Albert and this and that, and XLBERT and so forth. So ExcelNet. And very successful for their purposes. At the same time, the GPTs have also been very successful. When GPT-2 came out, it was supposed to be remarkably good. A lot of people were using it for a lot of things. Then came GPT-3, which is ginormous. I believe the exact numbers escape me, but it is in hundreds of billions of parameters. Right? The sheer thing is mind-boggling that you can make a model with so high, in such a high dimensional space, like so many parameter space. You're talking billions now, or hundreds of billions. So GPT-3 has been remarkable, as you know. So the basic idea that you should remember with these transformers is um, you give it some input, and in some sense it continues that. It's sort of, for example, language translation. You give it English, and it will, from the representation, it will produce a French. Or you give it a sentence, English sentence, and you say, what comes next? What is the next sentence that should come out of it? Right? And things like that. So now these transformers have been very effective, obviously, in the NLP domain, and we covered it in our NLP workshop quite extensively. They have also, we also talked about the visual transformers, the fact that computer vision has been completely dominated by CNNs, and the transformers weren't quite there. But then came the papers, and we have covered them, the 16 by 16 and so forth, in which you slice up the picture into little pieces, into little tiles, and you treat those tiles as tokens effectively as words. Right? 16 by 16 pixel, it becomes equivalent to a word. And if you treat it as a word, you can, the whole machinery of natural language processing and transformers that we had could be sort of reused. Right? That's the basic high level idea. So when you do that, the visual transformers, it began to appear that quite well they would achieve the state of the art or beat the state of the art. Right? And today we are now seeing quite a revolution in it's happening all around us. Computer vision is now heavily influenced by the so-called visual transformers. Right? And obviously CNNs are not gone. There is still a mixture of CNNs and attention in the mix, but certainly it isn't all CNNs anymore. It is visual, it is transformers and CNNs put together. So one of the prior work has been, so for example, if I show you a face, let's say, if I give you a face like this to the computer and ask the computer what comes next, right? Can the computer um, extrapolate and fill in the rest of the things and come up with this? Now, those problems are interesting. And one of the image, this thing here, work, GPT, does exactly that. You give it some image and it will complete the image. You give it a cat, it will do it. And the results are quite remarkable. It sort of forms a background. You show drops of water and you just show a tiny bit of ripple, and the transformer is able to infer that, oh, they are ripples, and it fills in the picture with beautiful, realistic, very physically realistic water drops falling into and creating ripples in water. Right? And when you see that, and maybe we should look at that also today a little bit, it is absolutely stunning that it understands the physical world so well. It gets the lighting right, it gets the shadows, it gets the 3D effects, it seems to get very realistic, including imperfections. And if you have a clock, sometimes the needles are crooked, the hands are a little crooked, so sometimes it will do all of that. So it makes very realistic things out of that. But the one thing that was there, that can we have produce images from textual description? So there has been a body of work. People obviously first start out by thinking GANs. Remember generative adversarial networks that we covered in the deep learning workshop. I apologize to those of you who haven't been part of that workshop.
Asif, are you sharing something
No,
or
no, no.
just the GitHub screen?
Yeah, I'm not sharing. I'm just talking at
Okay.
this.
Okay.
So, so anyway, I just apologize that some of the things I'm talking, it has background in the workshops that keep continuing here. So anyway, generative adversarial networks, if you remember, can generate fakes, deep fakes, and so on and so forth. Right. So initial effort to have somehow a text, give it a text input and produce images started out like that, the work of Reed, etc. And then there were variational autoencoders in the picture, so forth. And then this recent effort is remarkable. It's just absolutely remarkable. And we won't do the paper per se. What we will do is the basic idea of the paper is the same. We are just taking the GPT part of it, a simplified GPT model, just a 12 billion well, it's strange to say just a 12 billion parameter model. That is itself is a ginormous model, but not as big as the full GPT. When you take that and you play with it, I want to just walk through some of the results that you come up with. The first result they lead to. So what it is you give it text and you expect an output, a contextually relevant output from the transformer. And the fact that it can do things, and it can do things that don't even exist in the real world. That is what you expect the illustration industry to do, and very odd things. Like for example, a daikon. I believe in India we call it the muli, right? A vegetable. Can you expect? You can illustrate a baby daikon radish in a tutu, right? This tutu, I believe, is this funny dress, walking a dog, right? And you would not be able to find such an image on the internet, right? It's not an illustration anybody has thought of creating. And yet, from this sentence, look at the remarkable thing it does. It creates that. And it gets very interesting from here. And look at this. Here, we can change the word a baby daikon to avocado. So now all of a sudden, avocado is wearing this in a tutu dress or in a leather jacket. Do you see how it is able to produce realistic images? Now, see, given a description, there are infinitely many images one can produce. Technically, you say, and the paper uses a sentence like any textual description is an under specification for the image. In other words, you can produce lots and lots of images that are all in coherence with the textual specification. And you see that when I invite you to play with this, folks. Go to the blog, just play and think about how utterly remarkable it is. Now, in their website, they have given only things like this, in which you can play with a finite set of options. Right? Now, you may wonder that maybe has this transformer just learned the images? So what was it fed? It was fed pairs of text and image. Apparently, they didn't use any of the existing database. They scraped the web to find combinations of text and relevant images, contextually relevant images, and fed that into the transformer to train it, into the DALL-E to train it. And but then what it is doing is truly generative. It is not like just remembering from memory, oh, I remember this image on the internet and I'm serving that, right? It is truly learning and generating from that. So it has at some level, it has a comprehension of a visual comprehension from the text it has achieved. And that is the most remarkable thing, what it has built in its mind and understanding, which is in many, it is multimodal. It is not just pure textual understanding, which would be thinking in terms of word tokens and grammatic and structure, linguistic structure and so forth. It seems to have transcended that. It seems to have at some level understood the inner structure of images too, right? But the semantic structure of the images too. And it has created a unified understanding of the two, which is what is most remarkable about this particular breakthrough. So you can play with this. You can say leather jacket with a mustache. Well, here is a bunny with a mustache. And do you notice how fairly photorealistic it looks? It's an illustration here, right?
Asif, I want to chime in with a comment here.
Go ahead.
This capability,
Yes.
if available at an industrial scale, will wipe out the entire business of illustrators. The marketing illustrators, they're probably not even aware of these, but their entire business will get wiped out, because now if you're a marketing person and you have a script, a narrative in your mind, you can literally play your narrative out in text and see an image come up, and you can literally use that for your marketing.
Exactly. And it has just profound consequences. See, when these authors, when they write the paper, very interestingly, they mention at the top, they're aware that this will have profound societal impact. At this moment, they are sort of withholding the real source code, full source code of the paper, claiming that once the full societal impact is understood and its potential for harm, because it can also be abused, right? So, for example, we can say Premjit stealing the horse, and all of a sudden we have a picture that you present in court saying, "See, look here, Premjit is stealing a horse." Right? So, because it can do things like that, they're studying the impact. Potentially, I'm just cooking it up. I don't know if it can actually.
I think forensic science needs to keep up. So that's where Ratik is going to go.
Okay. So it just puts yet another twist to this whole deep fake stuff, right? But this is it, and people are worrying. They're already questioning. See, most of the time when we ask for illustration, at least for commercial and advertising, people are not expecting a Picasso kind of art. They just need illustrative art. And to your point, that illustration industry will have to reckon with DALL-E now. And the sheer creativity of DALL-E, just look at it. You can search for these images, reverse search these images on Google, and you won't find them anywhere, right? The sheer
But artists have a style. So does this produce a
right.
sequence of
Very
images in a particular style?
Very much so. So, Kyle, the style part actually is a very old solved problem. This is the whole. Anyway, so you in the deep learning workshop, we go through the whole thing. You give an artist's style, any artist, Picasso or Monet or something, and you give it any photograph, and you basically say, apply this style to this picture, and lo and behold, it will make. Quite literally, you will get a Picasso or whatever version, whichever artist style you want, perfect style copied into your photograph, and you will have a painting. In fact, that has become a big thing these days.
Neural style transfer.
Exactly, neural style transfer using GANs, generative adversarial networks. So we did that exercise actually, and this was part of our project. Can't you remember? Nice. It was.
Oh yeah. I just want to get it deployed somewhere where it won't break my bank. So I'm waiting for support vectors.
Right. So yes, go ahead.
Is there a certain level of specificity that like DALL-E will go to? Like I'm seeing, like a monkey or like a lemur. Is there like a certain level of specificity in terms of species that it can like go to?
See, here's the thing. They have trained it on a lot of images. And when they wrote this blog and they advertised this, obviously they're bringing their best foot forward. They have mentioned that there are some limitations we'll talk to. But in principle, it is limited by how much training data you feed it with. If you really want to focus on species of monkeys, right, then so long as you have trained it with those species, it will learn to distinguish between them and use them. But what we don't have from them is an open prompt in which you can add anything we want. Right? People have created there's a DALL-E mini project, GitHub, whose code is available. And I highly encourage you, in your particular case, I think that's what I expect you to do. Get started with the DALL-E mini source code, GitHub. The point with these things now has become that while they're breakthroughs, quite often the code is, once you understand the theory, it looks straightforward. The larger burden becomes training it with the right data. Can you find that level of data and train it with? If you have access to it, surely it will do it, at least in principle.
I see. Thank you.
So we'll go a little bit below. It says a professional high quality illustration of a giraffe. So you notice that a giraffe imitating a turtle, that would be the most absurd thing. And I don't think anybody would have tried it. So now a giraffe trying to look like a panda, right? Well, this one looks pretty interesting, and all of these, or a giraffe looking like a kangaroo. Okay. And if you look at it, what you get a sense is that if you ask a person to do it, they have to really understand giraffes and they have to really understand the structure of a kangaroo, right? Or the quintessence of a kangaroo. And it somehow seems to have blended these together, right? In a pretty fairly realistic illustration. And these are still illustrations, but then you say, well, these are illustrations, these are easy. What about, let's go a bit more, and we'll start, it starts out with illustrations. So you can see how it is able to generate emojis, literally emojis of any kind, creative emojis of right? And you have a laughing dragon fruit, okay? Or a scared dragon fruit, and so on and so forth. So you can essentially now create emojis out of anything, right? And you call this kind of learning is called zero shot, because you really didn't train it to do these things. You had just given it word pairs, contextual word and image pairs to learn from. But what it has learned to do is something beyond what it was trained to do, right? Which is the gist of the word. The word zero shot is sort of a extension or somehow almost a joke on one shot learning. So zero shot is we don't even need to do that.
Asif, have they exposed a grammar for this, like in terms of what is supported, what are the verbs and so on?
No, it's pretty open actually. The statement is you can use much of the common language. If you use an esoteric word they have not encountered, that's different. But from what I understand, because they have fed so much of the human language into it and so many images, it is fairly encyclopedic.
Okay. So you can talk in natural language and refer to reasonable amount of content in terms of like animals, and I'm seeing there are also a red cube on top of a green cube. It's able to understand positional
Yes,
signaling
of it and the 3D aspect of it. So, and that's what I want to go through. Like, if you really think how it does that, you get the understanding or the inkling that it is truly able to get a comprehension of real world objects, right? So in a way, real world objects can be described by a picture and by text, but somehow it has derived an understanding of it, which is the most remarkable thing. It understands 3D stereoscopic views of things. And I just want to go a little bit through this. So you can say this exact same cat on the top as a sketch on the bottom. So you notice that everywhere, these are images of cats, and here, well, not exactly cat, but dogs. And what it does is it says, make their sketches. So isn't it remarkable that it can sketch? It was never taught to do sketching. Remember, it wasn't taught to make sketches or anything at all. But from the textual language, it knows what sketching is. It has an understanding of sketching. And so it is able to translate this cat, into all sorts of sketches. Now, I hope you would agree that to me, they look pretty photorealistic. Some of them look odd. For example, this one looks rather odd, right? But this looks pretty realistic, right? This one looks pretty realistic to me. Right. And you can do, I actually like, because I have a golden retriever, so I am inclined to go with this one, right? So do you see it is able to do these dark sketches? But instead of sketches, here's something that I found more interesting. You ask it to do a close-up. Somehow, where is it? Photo reflection. Look at this animal in extreme close-up view. And it is able to sort of get a sense of how this animal would look in a very close-up if you had just zoomed your lens and seen it. Isn't that remarkable? I found that very remarkable, that it could do something like this. Look at this, where my mouse is, this picture. I don't know, this, having a golden retriever, and very similar, this isn't a golden retriever, but just some other dog, but still, to me, it looks very, very realistic close-up, isn't it? It even has a twinkle in its eye.
I hear the dog kind of approving, right? Dog bark.
Was that, Alvin?
I said a dog is barking in the background, so somebody's approving.
Yeah, that's my golden retriever. Giving her approval. And so anyway, this is illustrative. We'll talk about it and how it is done in the next session. With this session, I just want us to just see what the state of the art is and why it is very, very important, I suppose, these days that when you do machine learning, in the deep learning one, right, the transformers applied to computer vision now is a huge thing. So now, see, image completions, we already did, computer vision's classification. The remarkable breakthrough is that it can combine text and images tasks together in such a remarkable way, such a remarkably accurate way, right? This teapot was another interesting illustration. You have a teapot in the top with GPT written on it. So, well, it goes, do you see how, so this is the point I was saying, do you see how photorealistic it is? It even draws shadows and lighting, sorry, not shadows here, but even, yeah, here, in this one, you see shadows. It is so realistic, the lighting and everything it seems to be able to render. And if you just change it to this, it still gets it pretty realistic. So do play with this. And even if you give it a strange teapot, it seems to manage it. And you can sort of, it gets more interesting as you go down. So one of the biggest puzzles, Raven's progressive matrix, as you know, is an IQ test. Like if you're in the army, they'll test you with this and so on and so forth. If you want to be promoted in the army at one time, it used to be necessary. And it is supposed to be a quintessential human test, like of intelligence. And while people are dazzled by, you know, the fact that it can do all of this, what I found very interesting actually, is that it manages to fulfill this test, this Raven test. It can tell you the completions of what belongs where, right? So set B is here. So I don't know, example image prompt, it will ask you what should be here. Right. So if you look at this picture, there is this, there is this, there is this, right? And with a circle, with a square, with a circle, with a square, with a circle. So what should there be? There should be a square with a plus. So it comes up with a square with a plus, right? It's trying its best to do the completions. Right? And that is interesting that it can do. It can actually do well in IQ tests, which is quite remarkable. You give it a word, give me a photo of the food of China. We can say, let's try India for a change. And would you say that this sort of is the very realistic rendering of food of India? Anyone?
Yes.
Yes.
It's pretty, right? It's quite remarkable that it understands this food of India and it is able to do, you can say, museums in India, and all of a sudden it has the right images. Right? So this one, in a way, you can say, well, it may have memorized because it could have done. The remarkable thing is that it has, these things don't actually exist, right? It has synthesized from whatever images or understanding of museums of India it has and does it. But the point is that you see that there are so many combinations possible. Wildlife of India, deer is pretty common, so it has done that. Deer, right? And then you can say Bhutan. Let's say Bhutan is close to where I live, so I'll try that. Oh, amazing! So what you may not know is Bhutan is a mountainous country. Lots of mountains and extreme greenery, very mountainous, very, very green, and with terrace farming. And the remarkable thing is, do you notice that there is a hint of greenery and hills everywhere in this picture, except maybe this picture? Right? And all of these are synthetic images. And truly remarkable is it sort of knows this is how probably it looks. Now, I don't know the animals of Bhutan so well, but I know that some of these are goats and these things are pretty common there. So anyway, we'll talk about it when we do at this moment, this is just having fun with it. Alamo Square, San Francisco from a street at night. Okay. So it seems to understand lighting and composition. Right? Golden Gate Bridge and now this is different. Remember that in the transformer, you give the inputs and sometimes you give 2 sentences and so forth. So here you give a text prompt and you give it an image. So you say that the produce results where the top looks like this. So do you notice that all the tops look like this? And it has rendered the Golden Gate in all sorts of scenarios, right? To me, this one actually looks very realistic because I know this is the naval base from which I would take pictures. I've taken a picture similar to this. So obviously these are all very realistic images of the Golden Gate. But what happens if I choose something like this, right? And there is something, actually, I found this remarkable because my building was on the East Bay in Emeryville, a place, I mean, most of you who are here in Silicon Valley know, Emeryville, the tall Siebel building, the green building. I was lucky in the early days to have an office with a literally $1 million view. I would look out of the office and the sun would set on the Golden Gate, very much like this. And the interesting thing, of course, is that the sun moves because in different seasons. So I would see it set on one side of the Golden Gate and then over the seasons change and set at the other side of the Golden Gate. So this picture, when I looked at it, it was very reminiscent of what I used to see from my window, office window, for a long time. Very, very remarkable. So I would say that let's go play with it, guys. Let's appreciate the beauty of this. And then we won't be able to see we'll look at this code a little bit, but we'll try to do something with it in our, well, not in this particular course, but in the deep learning course when we do. And giving you a heads up eventually. We are going to do the deep learning course right now, but we now have deferred it to post-January. We will actually be writing our own little generators, text prompt and image generators, but we'll do it for very specific domains. This is all very good. The question is, how do you make it useful for something real? Right? How do you productize a functionality like this? So I throw this as a challenge to you to come up with ideas. Right? And think about it. One easy way is that suppose you have lots of Lego projects, Lego pieces or something. And can you say that, show me this, putting it together? Not Lego as in kids play, but as in machinery parts. Like, could you design something like this? Could you build something like this? So you can think about that. And there are many such ideas. It also seems to know history. And this was a remarkable fact. A photo of the phone from, and you give it a date. And the most remarkable thing is it seems to have figured out what the phones will look like. The amazing thing is it can even tell you the phone of the future and the distant future. These are its guess of the phones of the distant future, right? Which probably are wrong, but I'll let you guess. But I found it interesting that it could do phones of the past quite well. Right? And you can do with different lightings and so on and so forth. Right? So anyway, how does it do it? There are two aspects to it. See, when you take a picture, the picture would be, the pictures they took is 256 by 256. I believe 256 by 256, which is too big a picture. As you know, from our deep learning workshop, we don't have the computational resource. So what did they do? You remember variational autoencoders? So it uses variational autoencoders to come up with a much shorter representation of the image, 32 by 32. Once it gets a 32 by 32 image representation, that is a encoding. That effectively limits your vocabulary now to 32 by 32, which is about 8,000 something, right? Or 9,000 something. So effectively that becomes your new code book. In code book, if the word code book doesn't mean something to you, think of it just like words have dictionaries, right? The whole vocabulary, a word belongs in a vocabulary. In some sense, when you do computer vision, anything you do, or any picture that you see, you sort of try to relate it to, in quotes, a word in the vocabulary or sort of a entry in your code book, right? So that's the basic idea. Then the rest of it is somewhat straightforward. So the work of read, etc., use GANs. So here what they do is, once you have created a compressed representation, you have this, You create a single vector. Remember what goes into a transformer, a single token vector, right? And so they give 256 tokens for text and the rest 1024 token for the image part. And so they send in a token, a text and an image together into the transformers learning process, and that is all. That's it. I think that eventually, should they open out the whole source code, open source the source code, we'll see a lot of optimizations and a lot of details and so on and so forth. But fundamentally, what we'll see is, I don't think it would be something you would not have expected. But they have certainly thrown a lot of data at it to train it. Excuse me, 1 second. So there are quite a few, I would like to say as we finish it, a few paper or things that do. One thing that I liked very much is Yannick. It's a Yannick Kilcher. I have encouraged you folks to listen to his videos in the past also. He tends to write or create videos. He created this even before the details of the paper came out, but now the paper is there. At some point we'll review it. So, but I think he did an incredibly good job in pretty much guessing the paper before it came out, and in giving an illustration, or he thinks how it was built. And I think I agree with that. I'll post these links on our, and in many ways, this explanation is far more detailed than what you find in the paper. The paper has details, but this is even more detailed or so forth. So I'll put this there. And then there is Mini-DALL-E. Mini-DALL-E is, now this is available. By the way, don't try to run it on the website. It will always error out. They say you can play the same game on using the Mini-DALL-E, but what you can do you guys remember Hugging Faces? Hugging Faces was a repository of
Transformers.
Transformers, exactly. All sorts of transformer-based models are here. Since this is also transformer, so inevitably now there's an implementation of DALL-E in a mini form in Hugging Faces to be used. And it's pretty good. At least the good thing with this is you can actually go and read the source code, right? You can go and read into it and get a sense of how he has implemented it. And so it's pretty good, actually. It takes some time to read through it. So if you want to get a jump start, you can do it. And especially if you're doing a project with it, you certainly do that, right? Go through the source code. So very well, actually, I was going through the source code just now. Fairly well written. It's very neat and well written. There's no comment there, but when I look at the source code, all the variables and everything is very well described. The naming convention is good. So my feeling is that if you sit down for one day, morning to evening, you will get the whole idea. Assuming, of course, you understand your transformers and you understand your PyTorch. Right. So this is that. And anyway, so that is that. There's a paper, obviously.
Asif, one quick question there. So what is the purpose of the source code that they're making available? Because nobody can practically train this, right? So what does this source code essentially mean?
See, they haven't revealed the source code. The people have implemented DALL-E Mini on their own, right, based on the main theoretical ideas. But OpenAI is still very hesitant. See, they were very hesitant in giving the GPT-3 source code. Even here, there. And their claim is that this has a potential for massive social impact, that people should be given time to understand what the social impact would be for something that looks so breakthrough. And they have withheld it. But your question, should they release it? The question still remains that in this world, when to train this ginormous transformer model takes, all you need is only the big companies can do it, the likes of Google, OpenAI, which is a consortium of Microsoft and Facebook and all of these people. They all pour their hardware into it. Then only can you do it, because the amount of data that will go itself is ginormous to train this massive, massive transformers. Right? So you and I can't do it. And therefore the transfer learning part, right? Remember, if they release this DALL-E publicly, we could do that. Then the beautiful thing is that we can do transfer learning. Remember, in deep learning, we did transfer learning. Means we took this and we applied it to ours, the Tree Pilgrim project, all the other projects. So the good thing is once a transformer understands something so general, usually applying it to specific commercial things is a very short run. It's just fine tuning the transformer. For example, in my workplace at this moment, my team, we do a lot of things trying to understand from the text, especially learning material, which subject, which topic are they about. So we don't use, what do? We take families of birds, we fine tune them to our problem. We can't train bird from scratch. It's not possible. It will rake up a ginormous bill in the cloud. Right? So we are in a peculiar world. This AI is becoming more and more powerful, but the sheer hardware that is needed the cost is exponentially high. We are talking now of tens of millions of dollars or hundreds of millions of dollars to train this AI. Somebody told me that not just money, but the sheer environmental impact, the electricity consumed to train one of these AI models is such that it will shock any environmentalist. It's an environmental disaster, actually, to train one of these transformer models. Yeah. So obviously, we need fundamental breakthroughs. See, AI at this moment is a very young subject, especially this transformers and this ginormous deep neural network models. People are playing with things and being awe-inspired, awestruck by how amazing they are, what they create. But we don't have a full theoretical understanding of these things so that we can create a simpler one. So in another paper we'll do soon, remember we talked about the lottery system, right? That deep neural networks are fundamentally, they have a internal lottery based on the random initializations. When you train a neural network, what happens is that the entire network doesn't get trained according to this hypothesis. The lottery hypothesis essentially says that a subnetwork preferentially based on the random initialization becomes the one that does most of the learning, and it leads you to one specific minima, okay? One specific solution. If you think in terms of minima, like for example, only yesterday we were talking about the minima of the loss surface. And now for linear regression, it's beautiful. It's a convex loss surface. There's only one global minima and you can get there. In deep learning, you don't have a convex situation. So you have hills and valleys. If you remember the loss landscape paper, loss landscape work that we did in deep learning, what it showed us is that there are huge thousands and thousands of minimas, right? But then the remarkable thing is with all of this, that you don't have to ask for the absolute minima. Most minimas are close to the true minima. And not only that, there seems to be a path, there's to be ravines, riverbed ravines, connecting some of these minima. A very beautiful landscape emerges in that. And we did some lovely visualizations, if you remember. In fact, we started the deep learning with that, right? So that is that. I mean, at this moment, we are still beginning to understand it. So one question is that if only a subset of the network gets trained, then why are we spending electricity and so much of compute resources training the entire ginormous network? Is there a way we know beforehand that this is the short network we have to train and so forth? So there's a lot of work. It's a very active area of research. In fact, so active that while I'm speaking, it almost gets a feeling that you say that something needs to be done, and next day you hear that somebody has already been doing it and he has a paper on that. Right? So that's the fun part, I suppose, of deep learning and of machine learning in particular. The field is rapidly moving forward. So that is it for today, 7 minutes. Any other questions, guys?
No, fun romp.
Nice. Okay. So do play with it. It was a simple, because we also have in the audience people coming from the comprehensive data science workshop background who don't have a full background in deep learning. I thought I'll start by simply taking a blog where you can go and play around with the state of the art rather than dig deep into the technical aspects of it at this moment. All right, guys. Yeah. Bye then.